So today we start a new topic. It somehow develops the tools that we have discussed in statistics and also in econometrics. And we will talk about analysis of categorical data. So before we start, let's go briefly through the point where we are. So what we have covered already, because it has passed around 14 weeks probably since we started. And we have studied a lot, so let's give some brief overview of the material covered. So our main task is to make inference about the unknown population parameters of the studied variables. So we try to represent these variables in different ways. The simplest way, just a random variable with some distribution. In ANOVA, we built some simple statistical models that our random variable consists of three parts: population mean, the deviation because of the given level of a qualitative variable, and some error term. We also did similar thing in econometrics class when we represented our variable of interest as a sum of two parts. One is the conditional expectation, which depends on the other variable, and another one is the error. So all of these are related to the variables of interest and different models that we built about them. And our goal is to make some inference about the unknown population parameters. So the key step for application of the methods that we have discussed is to collect a random sample. So we are working with the data. This data must be collected through some random experiment. Ideally, if we don't have such an opportunity, then we need to come up with some other ideas. And the question about what to do if the random sample is not available is going to be discussed in the next subjects, so most probably in econometrics too. Then based on the sample, based on the data, we do the estimation procedure. We know three methods of estimation: method of moments, method of maximum likelihood, and from the last week we know also method of ordinary least squares estimation. With the help of one of those methods, there are more, not only these three, but much more different methods. So we estimate the parameter of interest. So we kind of make a best guess of the unknown population parameter. Then this estimate that we calculate is a particular outcome of a random variable called estimator, right? So this is a random variable. Why? Because it is based on the random sample. Therefore, we want to know the distribution of this random variable, which is called the sampling distribution. Unfortunately, it's not possible to build the sampling distributions for all, or at least it's much more difficult to build the sampling distributions for all estimators. Therefore, we do some other thing. So we get the appropriate test statistic, which has a known sampling distribution. Then we make hypothesis testing. So basically, with the help of the sampling distributions, we either build confidence intervals, and then we say that, well, with 95% confidence, we believe that this interval covers the population parameter, or we test some hypothesis. So that's what we are doing already during last 4 weeks, probably, or maybe 5. So we already know several types of hypotheses. One sample hypothesis about population mean, variance, or proportion. We know two sample hypotheses about equality of population means or variances of proportions. And last two lectures we discussed the test about the equality of several population means, either one-way ANOVA or two-way ANOVA. So every population is represented as the different interaction of levels of two factors, or if it's one-way ANOVA, just different levels of a given factor. So yes, populations differ according to the level of some qualitative factor, or populations differ according to the levels of two qualitative factors and their interaction. So that's actually where we are. So we have covered a lot of useful things, and whenever you are going to do some data analysis or data science things, this material must be known and must be applied. And let me also briefly remind you the algorithm of hypothesis testing, so it might be useful for the next, for the midterm, for the upcoming midterm in the next week. So how do we do this hypothesis testing? So we have done this many times, but once again, as a repetition. We state the null hypothesis. Usually null hypothesis represents no change or no difference between parameters. The alternative hypothesis usually represents the desired outcome or researcher working idea. So if you want to prove something that, I don't know, two population parameters are different, or there is a particular dependency between the quantitative variable and the level of some factor in ANOVA, usually alternative hypothesis is exactly what we want to show. Then we take the null hypothesis and we believe that this null hypothesis is true. And under this belief, we construct an appropriate test statistic. So we know a lot of them. T statistic, chi-square statistic, F statistic, Z statistic. And we introduced also, 1 week ago, we introduced the Q statistic, right? That was a studentized range distribution statistic. So, and there are much more of them. Then we state the desired size of a critical rejection region, also known as significance level or probability of type 1 error. So we denote this with alpha. And then we construct a critical region with the help of critical statistic. And we either check whether the computed test statistic falls into the critical region, and based on this we reject the null hypothesis, or if the test statistic doesn't fall into the critical region, we are not able to reject the null hypothesis. Or we can compute p-value, and we can compare this p-value with alpha. And whenever p-value is less than alpha, it states that the null hypothesis must be rejected. Whenever p-value is greater than alpha, usually 5%, we are not able to reject the null hypothesis. The same. So that's a repetition. Might be useful for your midterm, because as I promised, in the midterm you will have some hypothesis testing tasks based on the previous material. Maybe you have any questions here regarding the testing or regarding the previous material. No questions. Okay, so then let's start our today's topic. Yeah, the last point, sorry, I forgot. The last point, that we need to make a meaningful conclusion of the test. So it's not like we reject null hypothesis or we don't reject null hypothesis and that's it. You need to go back to your initial research question, what exactly you wanted to know with the help of data, and then you need to provide some meaningful answer. For example, with the help of the test, we see that there is no difference in oil extraction for different technologies. Or we see that a particular maintenance team, so I'm taking the examples from the previous lecture, the particular maintenance team leads to the lower oil extraction for all oil wells, something like this. Or the average number of cars for federal authorities has not increased from 2013 to 2020. So we had this example on the exercise session. So something that you need to state as the overall conclusion of your test. And this conclusion must be some story. So what you see in the data and what this hypothesis test provides you. This is a very important thing because we are not doing mathematics, or at least we are not doing mathematics only. We want to provide some economic, meaningful conclusions with the help of this mathematical tool. Therefore, this last thing must be always provided. And related to the midterm, I will be given points for the correct conclusion of your tests. Must be done. So, and now let's go to the material of today's lecture. The topic is called the analysis of categorical data. So let's try to understand what is the categorical data. What are we talking about? Well, many experiments can result in measurements that are qualitative or categorical rather than quantitative. So we are not able to measure something. We are not able to get a number. So a quality or characteristic is identified for each experimental unit. And the data that is associated with such measurements can be summarized by providing the count of the number of measurements that fall into each of the distinct categories associated with the variable. So let's see some examples to understand what we are talking about. Customer satisfaction. So you randomly select 100 customers visiting your supermarket, and then you ask them how you are satisfied with the service of our supermarket. And then they give you some answer: very poor, poor, neutral, good, very good. Well, the problem is that those are not numbers. We are not measuring these customers, right? So we ask them, and the answer is qualitative in nature. It's not quantitative. It's not like production of oil. It's not like the salary. It's not the number of cars. It's a qualitative answer, categorical answer, right? Very poor, poor, neutral, good, or very good. And for every customer, we write down the response, right? So customer 1 responded that he evaluates the quality or his satisfaction with our services good. Second customer, very good. Third customer, poor. Fourth, and so on. So we have a table, the list of 100 responses, and all those responses are words or levels. But what we are able to do, we are able to count how many people, how many customers responded very poor, how many customers responded poor, how many customers responded neutral, and so on. So we're able to count how many people said every of these words. And then the data will provide us the count of the number of measurements. So these are our measurements: very poor, poor, neutral, good, and very good. And then we count how many people responded in this way. Or employee gender, female and male. Do we have some numbers for this? No. Just one category, another category. How can we measure? How can we give this some quantitative sense, we can count how many female workers are in the firm, how many male workers are in the firm. All level of education, marital status, single, married, widowed, divorced. Right? So this is also the data, and this data is widely used in data analysis, in data science. And we need to establish some methods how to work with this data. So we will start with the definition of something which is called a multinomial experiment. If you remember, when we have two outcomes of this qualitative variable, like female and male, what kind of distribution usually we apply to such variable? When we have one or like one of the two possible outcomes, which distribution we usually associate with such variable? Who can answer? Once again, if you have a variable and this variable can take only one of two possible values, 0 or 1, what is the distribution associated with this variable? We don't have a lot today, guys, so you need to respond. You need to respond somehow. See, no, what kind of distribution do we use when variable takes one of two values, 0 or 1? What is the distribution associated with such variable? Do you remember? Well, so the data that we have discussed exhibits approximately the following characteristics. The experiment consists of n identical trials. So we make n trials, and the outcome of each trial falls into one of k categories, or we call them cells. The probability that the outcome of a single trial will fall in a particular cell will be denoted as pi. So I takes value from 1 to k, and it remains the same from trial to trial. So which means that if we randomly select a person, the probability that we select a married person, for example, stays the same. If we randomly select another person, the probability that we will select a divorced person stays the same for every other trial. The sum of all probabilities must be 1. Well, because of the definition of probability, and the trials must be independent. So the outcome of one trial does not influence the other trial, which is more or less logical when we talk about asking customers about their satisfaction. So the response of one customer randomly chosen, and then the other customer that comes to the questionnaire. So it's gonna be this that those are gonna be independent of each other. And we are interested in the counts for each category. So N1, N2, N3, and K are the numbers of observations that fall into the particular class or category. So Ni is the number of trials for which the outcome falls into the cell I. So the sum of these outcomes must be equal to the number of trials. Basically, if I ask 100 people, all these 100 people must be placed in one of the categories, either satisfied with the service, with very good mark, with good mark, with the moderate mark, bad or very bad. So the total number of people must be divided into 5 categories. And we define this as a multinomial experiment. We call this a multinomial experiment. So the experiment that ends up in one of k qualitative or categorical, one of k categories or cells. And the multinomial experiment is a generalization of the binomial experiment. So the binomial experiment is the experiment when we have 2 outcomes. Exactly what I was asking you. So for the multinomial experiment, we want to establish something which is called the multinomial distribution. So the multinomial distribution is defined in the following way. So if we have k probabilities, such that these probabilities sum up to 1, and each probability is not negative or positive, greater than 0, for every group or every class, then the random variables x1, x2, and so on, xk, so those are the counts, for every group have a multinomial distribution. So this is a joint distribution of k variables. This distribution has parameters n and from p1 to pk, and the distribution function is given like this, in the following way. If we reduce this to 2 groups, k equals 2, then we will get the binomial distribution. So this is the extension, or this is a generalization of a binomial distribution when k is greater than 2. And so we put some restriction that the sum of these x's must be equal to n, and i's, and also x I can take values from 0 to n. So x is the count, so we calculate how many times, so we count how many times a person responded with the answer good or very good or bad or something like this. And it might be from 0 to n, when n is the total number of people participated in the questionnaire. So as I said, the binomial distribution is a special case of the multinomial distribution when k equals 2. And so therefore, this multinomial distribution is somehow related to the initial question that we want to investigate, the analysis of categorical data, and the probability that particular response will fall into one of the categories. So in order to make our life simpler, we are not going to derive some maximum likelihood estimates or something else from this multinomial distribution. We will just derive, or not derive even, we just state some necessary properties of this multinomial distribution that will help us to establish the subsequent algorithms of hypothesis tests. So first of all, the expected value of a particular x, xi, is simply equals to n, the number of trials multiplied by pi, the probability that a given variable falls inside the category I. So the variance is calculated similarly to the binomial distribution. So basically the expectation is also similar to the binomial distribution. But we also have some dependency between these variables, so therefore we need to state the covariance. Covariance between xs, the number of counts falling into S category, and xt, the number of counts falling into T category. And this is calculated in the following way, more or less similar to the variance. Yes, just to make everything to use the rigorous notation, we will use, instead of xi, we will use ni. So this xi here and ni here are identical. But in order to give some meaningful notation related to the further problems, we will use this. But as I said, xi and ni are identical. And whenever we denote the random variable as xi here, it's going to be the same as ni in all our further discussion. So let's take some particular example to understand what's going on. Suppose that we have an investor, and this investor is interested if there is a higher likelihood that the company publishes its financial report on a particular weekday. So we have 5 working days: Monday, Tuesday, Wednesday, Thursday, and Friday. And we want to know if there is a higher probability or higher likelihood that companies tend to publish their financial reports on a particular weekday, for example, on Friday or some other weekday, maybe Wednesday. So this person collects a sample of 150 randomly chosen public firms and records the weekday when the financial report was published. And then we have, as an example, the following table. So these are 5 categories: Monday, Tuesday, Wednesday, Thursday, Friday. Those I's, I1, I2, I3, I4, I5. And we count how many firms publish their reports on Monday, how many firms publish their reports on Tuesday, how many firms publish their reports on Wednesday, on Thursday, and Friday. So we see that on Wednesday, there are less firms who publish their reports. On Friday, more firms publish their financial reports. We can suggest that probably firms want to publish their financial reports on Friday. Maybe there is some particular reason. We can tell a story that firms publish their financial reports on Friday. Why? Because on Friday there is a weekend next, and so probably the investors will have more time to read the news, and if the reports are not very optimistic, they will not be able to sell the stocks immediately. Maybe there are some other reasons. But we see from the data that Friday tends to be slightly higher than other days, and Wednesday tends to be slightly lower. But we still remember that we are working with random variables, and our sample is random. So therefore, these outcomes might be such because of the randomness of our sample. And the question is whether this data suggests that the difference in the number of these published reports depends on a weekday, or this particular difference appeared because of the randomness of our sample. So this is the usual way how we visualize such type of data, a pie chart. We see the proportions of firms who publish their reports on Monday, they're 19%, Tuesday 23%, Wednesday 13%, Thursday 17%, and on Friday 27%. So we see that the majority of firms publishes their reports on Friday. Once again, the question is, do we have enough evidence to claim that this is a tendency and this is not just because of the randomness? So, according to the algorithm of the hypothesis testing, we will start with the initial belief. So, and as usual, initial belief that there is no particular dependency between a weekday and the publishing of the financial report. So the initial belief is the null hypothesis. And according to the multinomial distribution, the null hypothesis is going to be the following. If you have 150 firms, it's n. If you have 5 working days, and those are the categories that our variable can take on, the probabilities that we will fall in a particular category is going to be, the probabilities are going to be equal, p1 equals p2 equals p3 and so on, and it's going to be 0.2. So we believe that the probability that a firm publishes its financial report on Monday or on Tuesday, on Wednesday, and so on, these probabilities are the same. This is the null hypothesis. Well, the expected number of reports out of this 150 that falls into the particular day must be calculated simply as 0.2 times 150, and that's going to be 30. So we expect to see every day 30 reports out of 150. If there is no difference in probabilities of publishing these reports, we expect here, 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 and every other day to observe 30 reports. This is the expectation, right? So if there is no difference in the number of published reports, we expect 30 reports on each day. So now, this is the null hypothesis. The question is, once we have a null hypothesis, well, the alternative is going to be that there is a dependency, or there is a difference between probabilities. We will state this formally a bit later. But the question is, what kind of statistic we can use here? So usually for the hypothesis test, we want to have some statistic, as we discussed, t, z, f, chi-squared, whatever. So which statistic is appropriate here? Well, first of all, if the null hypothesis is true, then the true counts, the observed counts, ni, must not deviate greatly from their expected values np. Which means that when we look at this table, and when we see numbers here, 29, 34, 20, the deviations from 30 must be small, if the null hypothesis is true. So the deviation here is only 1, okay, from 30. Deviation of this is 34 minus 30 is 4. We don't know whether it's large or not. The deviation here is 10. Well, 10 probably is large deviation. Here is 6, here is 11. So we don't know whether these deviations are large enough to reject the null hypothesis. But at least this is logical, to observe the deviations from the expected number of counts, and then to incorporate these deviations somehow. So what do we do? It is reasonable to use a test statistic that involves all these k deviations, and the deviation is defined here. So as I demonstrated you, we look at the observed number of reports published, and we subtract the expected number of reports published. And we do this for every group, and then we want to incorporate this somehow into the test statistic. How can we do this? Well, more than 100 years ago, a mathematician, Carl Pearson, proposed the test statistic, which is a function of the squares of the deviations of the observed counts from their expected values. So we need to take these deviations, we need to square them, and it looks more or less similar to the sum of squares that we have discussed during the previous lecture. But we weight this sum of squares by the reciprocals of their expected values, like this. So we take the observed value, we subtract the expected value, we square this, and divide by the expected value. And then we sum all of them in order to get this test statistic. So this is a test statistic. The next question is, what is the distribution of this test statistic? When n is large, when the number of trials is large, this statistic has an approximate chi-square distribution. Again, it's approximate because it is built on the asymptotic theory. It is built on the idea that this statistic converges a distribution to the chi-square distribution. So we are more or less done. We have the test statistic. We know how to calculate this test statistic. We know the distribution of this test statistic. Everything is ready in order to make the test. But we need to make several notes on this test statistic. So first of all, the cell counts Ni should be at least 5 in order to use chi-square. So we must verify that every number here is at least 5. If it's less than 5, there are other methods applied, which are beyond of the scope of our course. But we still must verify that these numbers are greater than 5. Then, chi-square distribution has two parameters. One parameter is, sorry, not two parameters, basically one parameter. This parameter is the number of degrees of freedom. Well, which means that we need to know what is the appropriate number of degrees of freedom associated with the chi-square distribution. So the rule is the following. The appropriate number of degrees of freedom equals the number of cells, k, so how many groups we have for the data, less 1 degree of freedom for each independent linear restriction placed on the cell probabilities. So what does this mean? We always have at least one restriction. At least one restriction is that sum of cells probabilities must equal 1. This is always applied. We know this, that probabilities must be equal to 1. Therefore, we always subtract 1 from k. The rest is going to be applied if we must estimate the unknown parameters required in the calculation of the expected cell probabilities. So in this case, when we state the null hypothesis, no additional estimations are done. We just state, well, probabilities for every cell equals 0.2. That's it. But if, for some reason, if we want to calculate these probabilities, we need to first estimate something else, then for every estimated parameter, we reduce the number of degrees of freedom by 1. And we will see the example, how this works. So the degrees of freedom is reduced by 1 for each parameter estimated, if you estimate something else. Then the question is, what kind of alternative hypothesis do we use? Because we want to know how to build the critical region. Well, because we want to observe in the data large differences between observed and expected cells counts, we will reject the null hypothesis only when the test statistic is large. So therefore, we apply the upper-tailed statistical test always for this case. So what must be taken from this slide is that we must be careful when taking the number of degrees of freedom for this test, and this is called the chi-square statistic. and chi-square test. And the alternative is always upper-tailed. The same story as for f-test when we apply well, ANOVA, or when we apply the test of equality of two variances. So now how this test looks like. In general, the null hypothesis, in general, it's not like the null hypothesis about our example, but in general, we need to state the probabilities attached to every cell or to every category. So probability that we will fall into the first category is this. So it's just P1, 0, which means that this is just some number, like 0.1, for example. Probability to fall into the second cell is P2, 0. Again, so that means that this probability equals to some other number, 0.5. And probability to fall into the kth category equals to also some number. Yes, pk0 denotes a specified value for pi. The alternative hypothesis is such that at least one of these equalities does not hold. At least one probability is not equal to the stated value. So we know what is the test statistic. We know how to calculate it. The critical region for the upper tail alternative is such that this test statistic must be greater than a critical value. And the critical value here is the quantile 1 minus alpha quantile of a chi-square distribution with k minus 1 degrees of freedom. And the number of degrees of freedom reduced by 1 because there is only one restriction, p1 plus p2 plus blah 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 plus pk equals 1. So now let's see our example and let's try to go through the calculations for the example. Well, we know that the observed number of reports published on every weekday is here, 29, 34, 20, 26, 41. We know that under the null hypothesis, the expected number of reports published, if there is no particular deviation, or there is no particular difference in probability that the report is published on Monday, Tuesday, and Wednesday, and so on, is going to be solid. Now we calculate the chi-square statistic. The observed value minus expected value squared divided by 30 for the first category. The observed value minus expected value divided by expected value squared for the second category, and so on. So we do this for every category. So now we have 5 terms because we have 5 categories. The chi-square statistic is this, 8.467. Now, number of degrees of freedom, 5 minus 1. 5 categories minus 1 equals 4. The critical value of a test statistic is 9.48 or 49 approximately, 488. So we use, as all the other lectures, we can do this with the help of Python, right? Stats, guide to PPF, and then this calculation. So the critical region, therefore, is chi-square greater than 9488. And we look at the calculated test statistic, we look at the critical region. So what do we see? We see that the test statistic does not belong to the critical region. Maybe somebody else wants to make a conclusion. So what does this mean? That we have this critical region and we have this test statistic, and we see that test statistic does not belong to the critical region. What does this mean regarding the statistic, regarding the hypothesis test? Guys, I'm giving you a chance to make up for your failure in the beginning of the lecture. So nobody wants to make up. Okay. So this means that we cannot reject the null hypothesis. And since we cannot reject the null hypothesis, the likelihood that the company publishes a financial report does not depend on the weekday. So we don't have enough evidence in the data that there is a particular dependency between a weekday and the fact of publishing the financial report. Well, we are able to calculate p-value as well, and based on the p-value, so probably it's going to be close to 5%, so maybe at the 10% level of significance we would be able to reject the null hypothesis, but at least at this 5% level of significance we are not able to do this. So this is the logic. This is the logic of testing whether there is a particular dependency between the categorical variable and some kind of behavior of a firm. In this case, when the firm publishes its financial report. That's the simplest possible example of a chi-square test. Now, we can extend this somehow because the previous test seems to be very useful. With the help of this, we can specify some probabilities under the null hypothesis, and with the help of these probabilities, we can test whether the data observed satisfies the following probabilities. And we will introduce the extension of the previous test of the chi-square test, which is called goodness of fit test. How can we use this test? And why do we want to use this test? Well, basically with the help of this chi-square statistic, we can test if the sample data indicates that some model for a population distribution doesn't fit the data. You remember we always assume, or in most of the cases we assume, that the data is normally distributed. We also had one example back in lecture number 4, I guess, or 5, when we assumed that the number of transactions on the Moscow exchange are distributed according to the Poisson distribution. Well, we can test if the data fits our assumption about a particular distribution. And this is called a goodness of fit test. And the logic is completely similar to the chi-square test. So all the calculations, all the techniques used are the same. The only thing that we need to make several additional steps. So we need the observed and expected counts. And the expected counts now must be calculated as the same way, it's NPI, but this probability PI is calculated either with the help of the probability mass function or cumulative distribution function, so depending on whether we have discrete or continuous random variable underlying the data. So usually in this case, in order to get this PI, we must estimate the unknown parameters of distribution. And let's look at the example to understand this case. Well, in the lecture number 4, we had this example when we estimated the parameter lambda of a Poisson distribution. And we assume that the Poisson distribution is the appropriate distribution for the number of transactions occurred over a particular time interval, 1 second, on the Moscow exchange with Gazprom stock. So we had this table when this is the count of transactions, 2, 3, 4, 5, 6, 7 transactions over the second. And here is the count of seconds within a given trading day when this transactions occurred. So basically, if we take the whole trading day, if we divide this trading day into seconds, then in the whole trading day, we observed only 4 seconds when only 2 transactions occurred. We observed 9 seconds when 3 transactions occurred. We observed 150 seconds when 6 transactions occurred, and so on. So we have something similar to the previous table, to the table about the number of reports published. So we have counts here and we have categories here. So those are just different categories. So we estimated lambda that time. So lambda hat was 14.98. But the question, does this data fit the Poisson distribution, is still open, because we assumed that this data comes from the Poisson distribution. But we never checked, or we never tested whether this Poisson distribution is appropriate to model our data. So here is a time when we can do this. But we need to calculate, similar to the previous test, we need to calculate the expected counts for each cell. So what is the expected count for cell number 1? So instead of 4, how much would we expect if lambda would be 14.98? So this is n, and n is 28,800. Those was the number of seconds during the particular trading day, multiplied by the probability that x equals 2. If we believe that x depends on the x has a Poisson distribution, then we can use the probability mass function for the Poisson distribution. It's here. So we calculate the probability that x equals 2 with the help of the probability mass function for Poisson distributions here, and then the expected count for the cell number 1 is going to be 101. So we observe 4 seconds when only 2 transactions occurred, but we must expect only 101 second when 2 transactions occurred. Expected count for 3 transactions is going to be 503. We calculate this in the same way, but now instead of 2, here we plug 3. So the observed number is 9, the expected number is 5.03. For the third cell here, we plug 4, and the expected count is 1884. The observed is 29. And so on. So we do this for every cell in this table, and then we see, or we must be able to see, the observed counts and expected counts. So for every xi, we do the same. So after all, we will have something like this. So I reduce this table, of course, in the middle. So we will have observed counts and we will have expected counts. Here we are. And now we have the same table as we had in the first example. We have several categories, 32, I guess, categories. We have observed counts for every category, and we have the expected counts for every category. So we calculate chi-square in the same way, observed minus expected divided by expected, and squared numerator. Observed minus expected squared divided by expected, and so on. For every group, we do the same. Then the overall test statistic is 57.48. The number of degrees of freedom. And now there is a trick here. We have 32 categories. but we reduce it by 1 2 times. First time, -1 degree of freedom because of this restriction, so the sum of probabilities must be equal to 1. And -1 more degree of freedom, because in order to calculate these probabilities, pi, we estimated lambda hat. So lambda hat is not given, lambda is not given, sorry, but we estimated lambda hat, and then we use this in order to come up with these expected values of probabilities. Therefore, we reduce degrees of freedom by 2, not by 1 as in the previous example. The critical value of chi-squared is 43.77. The rejection region or critical region is any chi-square statistic, which is greater than 47.77. We see that.
Sorry, but why he is 32, not 33?
Because the number of categories is 32. We start from 2 here, not from. So we see that there is no 1. There is 2, and kind of the number of categories is 32 in this case. Okay.
Oh, I still don't understand why -1 and -1 again. I think maybe it's.
Let's go back. Let's go back. It was here. So we reduce 1 degree of freedom for each independent linear restriction placed on the probabilities. Look, one restriction in this case that probabilities must sum up to 1. This is one restriction. Another restriction that we estimated lambda. So with the help of data, we estimated lambda. And for every estimated parameter that we used, look, this lambda is not a population parameter. This lambda is the estimate of lambda hat is the estimate of a population parameter. This is the outcome of a random variable. And this was built, the whole estimation. So if you want, you can just revise the lecture number 4, how we did this. I illustrated method of moments and method of maximum likelihood with the help of this example. But the idea is that we got this number from the data with the help of the data. And therefore, this is the second reduction in the degrees of freedom. So first reduction regarding the probabilities, and the second reduction is because of the estimated parameter here. Why do we need this estimate? Why do we need this lambda? Because we need to calculate these probabilities. Without lambda, we are not able to calculate probabilities to observe probabilities that we will fall into the particular category. Look, in the previous example, we didn't need this, because in the previous example, our null hypothesis was stated as just all probabilities must be equal to 0.2. All probabilities are the same. We stated these probabilities because we wanted to test if these probabilities are equal or not. In the case of this example, the probabilities for the null hypothesis are not given. We don't have this null hypothesis. Our null hypothesis is different. Our null hypothesis is that the underlying probability distribution for this variable is a Poisson distribution. But if we want to calculate these probabilities for the Poisson distribution, we need to know lambda. We don't know the lambda. We don't know true population lambda. Therefore, we estimate this lambda first. We did this in the lecture number 4. And then, with the help of this lambda hat, we will be able to calculate these probabilities. probability that x equals to 2, x equals to 3, 4, 5, 6, 7, 8, 9, 10, up to 33. So basically there are going to be 32 calculations. Look, not 31, not 33, because we start with 2. So how many groups are going to be here? 32, not 33. Be careful. We have 32 groups here. And then when we calculate the degrees of freedom, so this is a typo. It must be k minus 1 minus 1. Yes, so this is a type. This is the correct. So we take k, 32 minus 1 for this restriction, minus 1 for this restriction. In total, we have 2 restrictions, and therefore we reduce the number of degrees of freedom by 2. 32 minus 2. This is the typo. It must be k minus 2. Okay, is this clear now?
Yes, maybe. Yes, I understand. Thank you.
Perfect. Thanks for asking. At least some interaction. So the critical value, the critical region. So now we see that the test statistic belongs to the critical region, and we also can calculate p-value. And based on the critical region, based on the p-value, we can state that the null hypothesis is rejected. The null hypothesis in this case, so sorry, I forgot to place this null hypothesis in this case, but the null hypothesis was that our data has a Poisson distribution. And we reject this null hypothesis, which means that our initial data, our data contradicts the hypothesis that the number of transactions occurred every second on the Moscow exchange follows the Poisson distribution. So the data presents a sufficient evidence to contradict the hypothesis that X possesses a Poisson distribution. So unfortunately, we used the data. We assumed that this data is distributed according to the Poisson distribution. We estimated lambda, but it turns out that the data contradicts our assumption about the Poisson distribution. So we need to come up with some other distribution that fits the observed data. We can do the same testing. We can assume, first of all, that the data is normally distributed. We can do the same test, check whether it contradicts the hypothesis of a normal distribution or not, and then calculate something else. But at least we are sure now that the data was not distributed according to the Poisson. And you can do the same test, goodness of fit test, for any other distribution. So you can check whether your data contradicts the distribution or doesn't contradict the distribution. Normal distribution, binomial distribution, exponential distribution, whatever. So we'll see the examples on the exercise session. So, and the last part of this lecture, where we can use the chi-square test, so probably the most interesting part, is called contingency tables. So what are we talking about? So we may want to assess the independence of two methods for classification of subjects. Or speaking simply, we want to test whether two qualitative variables are somehow dependent on each other. So, for example, we may classify a sample of people by gender and by opinion on a political issue in order to test the hypothesis that opinions on the issue are independent of the gender. So, opinion is categorical variable, gender is categorical variable, and we want to test whether one variable is independent of the other variable, or whether there is some dependency. Or we may classify, basically this task appears often in the practice. We might classify bank borrowers according to their marital status and their debt management in order to see if the probability of default depends on the marital status of a borrower. So the marital status is the categorical variable again. So it's like single, married, divorced, widowed. The debt management is also categorical variable, defaults or not defaults. And we want to know whether one categorical variable depends on the other. So in both examples, we want to investigate a dependency or contingency, that's why contingency table, between two classification criteria. So let's take a particular example to understand the task. Suppose a risk manager wants to know if the probability of default depends on the marital status. So the last example from the previous slide. She collects a sample on 300 borrowers, and for each borrower, she registers a marital status and whether borrower failed to meet the payment obligations in the past. So basically defaulted or not defaulted. And the resulting contingency tables is here. So yes, there is a typo, it's 500 borrowers, not 300, sorry, it's 500. So let's see, what do we have? We have a table. Inside the table, as before, as in the previous examples, we have counts. How many people, how many borrowers defaulted or not defaulted. So for example, 19 there are 19 borrowers who are single and who had default. There are 48 borrowers who are widowed and they did not have default. There are 2 divorced borrowers with default, and so on. So every number here in this table shows us how many objects, in our case it's borrowers, had the 2 characteristics. And then we have totals. So this is the total number of single borrowers in the sample, total number of married borrowers in the sample, total number of defaulted borrowers, total number of not defaulted borrowers, and of course the totals here must equal to 500 and the totals here must also sum up to 500. Yes, once again, sorry for the typo, it must be not 300 but 500 borrowers. We can also make some visualization to this data, and we can see that the fraction of single borrowers from those who defaulted on their loans is 50%. So kind of half of people who defaulted are single. 37% of borrowers who defaulted are married, and very small fraction of those who defaulted are either widowed or divorced. Among the people who who did not default, we have 42% of single and 20 or almost 30% of married, and larger fraction of divorced and widowed. Once again, as it was in the first example, we see from this picture that there is, or we can suggest, we can assume that single people and married people probably have higher chances to default on their loans, right? So why do we want to know this? Because if this such client comes to your bank and then you kind of ask him or her to fill in some questionnaire, you can see, well, this person is single, so the probability that he will not or she will not manage the loan properly is greater. If this person is divorced, let's say, then there is a higher chance that this person will not default, right? So this is the simple predictor of some probability. But once again, this difference between the two pie charts for defaulted and not defaulted clients may be just because of the randomness of our sample. So we randomly selected such borrowers that showed us this difference. And we want to test, do we have enough evidence in our data in order to claim that yes, the marital status somehow affects the probability that the person will default. So how we can do this? Again, with the help of the chi-square test, but now we need to come up with some trick how to calculate the probabilities in order to calculate the expectations. So we need to remember something from probability course first. The null hypothesis that we will state in this test claims that the default is independent of marital status. As usual, the null hypothesis is stated in a way that there is nothing to talk about, right? So there is just a random difference in the observed numbers, but there is no some rule or tendency. The alternative is that two categorical variables or qualitative variables are dependent, right? So the alternative is going to be such that the probability of default depends on the marital status. So formally, H0 is that column classification is independent of row classification. So the probability that you will fall in one of the column groups is independent of the probability that you will fall in one of the row groups. So let's denote PS the unconditional probability that the marital status is single. So unconditional means that this is just you randomly select the person, ask this person whether the person is single or not, and then the person responds, and then this is the probability that the person responds single. Similarly, PM, PW, PD are the probabilities that the person is married, the person is widowed, the person is divorced. So definitely these probabilities must sum up to 1, because the person must fall into one of these 4 categories. Also, similarly, we denote PDEF and PNDEF the row probabilities that the client defaulted or not. Okay, so the probability that the person will default, the probability that the person will not default are these ones. And their sum must also equal to 1. If the two classifications are independent of each other, so remember the probability. So this is the probability of one event. So the event is that we ask a person, a random person, about marital status, and the event is that, well, the person will answer that he or she is married, or he or she is single. This is an event. Another event is that we randomly select a person and the person responds whether he or she defaulted or not defaulted. This is another event. And from the probability theory, we know that two events are independent of each other if probability, well, the cell probability, so the probability that you will select single not defaulted person equals the product of row and column probabilities. So like this. Probability that you will select a single and defaulted person is gonna be equal the product of probabilities that the person is single, unconditional probability, and the person is defaulted. So we did this in the lecture number 3 or 4 of the probability course. If you want, you can revise. All the lectures are available. The problem is we don't know these true probabilities, right? So these true probabilities, PS, PM, PW, PD, P default, P not default, those probabilities are not known to us. And as usual, if you don't know some population parameter, we must estimate this population parameter. So here we are, the logic of our next steps. We must estimate the row and column probabilities in order to estimate the expected cell frequencies. So the estimated expected cell frequencies must be substituted for these in chi-squared statistic. So we want to calculate expectations, but in order to get these expectations, we want to know probabilities. We don't have probabilities because we don't know the true probabilities. We want to estimate them with the help of data. And so this is out of the scope of the lecture, but the maximum likelihood estimators for any row or column probability is found in the following way. If Nij is the observed frequency in row I, column J of the contingency table, so let me show you what we are talking about. So for example, here, like 137. This is N 2, 2. So second row, second column. 82. This is N 2, 4. Right? Or 3. This is N 1, 3. So this is the object that we are talking about. Yes, so this is the observed frequency in row I and column J of the contingency table. Pij is going to be the probability that your observation falls into this cell. Probability that the person is single and defaulted. Probability that the person is widowed and not defaulted. Something like this. So and is crucial here. And then, if observations are independently selected, then the cell frequencies have a multinomial distribution, as usual. So we have how many categories? We have 1, 2, 3, 4, 5, 6, 7, 8 categories now. So we fall into one of these 8 cells. And this is again multinomial distribution, and the probabilities for this multinomial distribution are derived in the following way. Are estimated in the following way. So the estimated, you see P hat, this is the estimate. Pij is Nij divided by N. So we take the number of people who are widowed and not defaulted, 48, and divide by 500. That's going to be the estimate of the probability that the person, a randomly chosen person, is widowed and not defaulted. Like this, 48 divided by 500. So this is our estimate of the probability that the randomly selected person is widowed and not defaulted, 9.6%. Or we can take 195 divided by 500, 0.39. So the probability that the single and not defaulted person is randomly chosen is 39%. So those are estimates of probabilities. For the row probabilities, we do the same out of the slide. Yeah, but okay. So if the probability for row I is given by Pi, so it's not Pij, but just row I, and Ri denotes the number of observations on row I, the maximum likelihood estimate of Pi is here, so it's Ri divided by N. So basically here, if we have two rows, this is one row, this is the second row, default and not default, what is the unconditional probability or estimate of unconditional probability that the person will default? We take 38, divide by 500. So 7.6% that a particular person will default, no matter what is the marital status is. What is the probability that we will randomly select a married person, no matter whether it's defaulted or not person? So the estimate of this probability is 151, this column total, divided by 500. So it's 30%, almost 30.2%. So that's what we are doing. With the help of this table, we estimate all these probabilities, row probabilities, column probabilities, and the probabilities inside. And then we do the following. So the estimate of the expected cell count equals to n, so the total number of observations, multiplied by the estimate that we are in the first row, probability that we are in the first row, and estimated of the probability that we are in the first column. Those two must be different, right? Probably I must put here some dots, whatever. But okay, so what is the probability that we fall into the particular row? We divide the number of row counts by the total, n. What is the probability that we will fall in the particular cell? Well, estimate of this probability. We take cell count divided by n. And then we can cancel n in numerator and denominator, and finally this expected value is this, R1 times C1 divided by n. So what does this mean? Let me show you an example just to understand what's going on. So this is our table, and now how can we calculate the expected number of people who are single and default under the hypothesis of independency? So we take 214 total of this column, multiply by 38 total number in this row, and divide by the total number of observations by 500. So 16.26. So this is the expected number of people who are single and defaulted. We do the same for every cell. We take 214, multiply by 462, divide by 500 in order to get 197.7 as the expected value for this cell count. We continue doing this for every of these 8 cells, like this. So the expected number of people who are single and defaulted, 214 times 38 divided by 500, 16.26. Expected number of people who are single and not defaulted, 214 times 462 divided by 500. Expected number of people who are married and defaulted, again 151, the column total times 38 row total divided by 500, and so on. So we repeat this for every cell. Finally, we will get the following table. The totals must be the same, definitely, right? So these totals must coincide, but the observed values are gonna deviate from the expected values. And now we have everything ready to apply the chi-square test, because we have observed values in this table, and those are 8 categories, and we have expected values for 8 categories here inside the table. So here the observed frequencies, here the expected frequencies. Now regarding the degrees of freedom. So degrees of freedom in this particular test are calculated as the number of rows minus 1 times number of columns minus 1. So we have 2 rows. We have 4 columns here. So therefore it's 4 minus 1 times 2 minus 1, which is 3 in this particular case. Again, this is just a rule how in this case we need to come up with the number of degrees of freedom. This is the critical value of chi-squared. And here is the calculation of the actual chi-squared statistic. So we take observed minus expected squared divided by expected. Observed minus expected divided by expected, and so on. So we are doing this for every cell. It's 4.57. So the critical region is any chi-squared that is greater than 7.8. We see that the test statistic does not belong to the critical region. Therefore, we don't have enough evidence to claim that probability of default depends on the marital status. So the data does not have enough evidence in order to claim this. So in this lecture, we went through 3 different examples how we can apply a chi-square test. The logic of this chi-square test is the same always, but the tricky part is how you come up with the probabilities under the null hypothesis. Either these probabilities are stated by you, like in the first example, or if you need to estimate these probabilities and you need to estimate some parameter in advance, then there is going to be another example. It's goodness of fit, and with the help of this you can check whether data is reasonably modeled with the help of some probability distribution. And lastly, we can apply, which is very interesting application, I think, we can apply this chi-square test in order to verify if 2 categorical or qualitative variables depend on each other or not. So for example, if the probability that the person will default depends on the marital status. And here is some wrap up which techniques we apply when we want to verify the dependency between variables, depending on the type of these variables. Look, if our dependent variable is quantitative and continuous, but independent variable is qualitative or discrete, we apply ANOVA. So remember, our independent variable was like the factor was, for example, the technology applied on the oil well, or the maintenance team, or something else. So you have some qualitative variable that categorizes the data into one of several groups. But the dependent variable is quantitative and continuous. We measured the production of oil by every particular oil well. If we have as dependent and independent variable 2 quantitative and continuous variables, we apply linear regression. So thing that we are discussing in the econometrics classes. So finally, if both variables are qualitative, marital status, independent variable, default, dependent variable, and both are qualitative or categorical, we apply chi-square test. So I guess that we have covered almost all possible variations of dependent and independent variable. Well, yes, the only thing is when independent variable is qualitative, but when dependent variable is qualitative, but independent variable is quantitative and continuous, right? But we will be talking about this maybe in the second econometrics. There's the fourth way. of the relationship, right? If your dependent variable is qualitative, but independent variable is quantitative. So that's it for the analysis of categorical data. Let me remind you that, first of all, I promised to place the sample of a midterm, and tomorrow you will find it on the course page, just to understand what to expect from the midterm. So I will give you some example with questions, and you will have a chance to go through this. On the exercise session, so next week you will have two, on Monday and on Wednesday. So on Monday there is some makeup, as I understand, on Wednesday the usual one. So on Monday you will go through the exercises based on this analysis of categorical data. And on Wednesday exercise session, you will go through the solution of this sample midterm. So we'll have a chance to ask some questions, clarifications, and you will see what are the correct answers. You can compare your solutions with the correct answers. Then next Thursday lecture time slot, you will have a midterm. So as I said, the midterm is going to be similar to the sample. And in any case, for the midterm, you need to know Python, at least those tasks that we have covered during our tutorials and on the exercise sessions. So everything that you have used for the exercise sessions, everything that you have used on the tutorials, like calculation of the mean, calculation of the variance, and the ANOVA tests that you performed on the last tutorial, those are going to be needed. Unfortunately, without them, you most probably will fail the midterm.